Hello and welcome to Building a Simple Neural Network for Classification. Today I'll be building, training, and evaluating a simple feed-forward neural network, FNN, using a major deep learning framework. I'll be examining the MNIST handwritten digits dataset, which is a 28 by 28 grayscale image dataset, uh, essentially the numbers 0 to 9 used to train a neural network. Now I'm going to pause here because I have, um, oh, it is the correct Jupyter notebook, never mind. Okay, so the first thing we're going to discuss then is loading the data, flattening it, and one hot encoding the labels. We'll build this simple FNN using the following characteristics. A 784 neuron input layer, 2 hidden layers, which are going to be using the RELU, or rectified linear units activation function, and an output layer of 10 neurons. And for that, we'll be using the softmax activation function. We'll be using a suitable loss function for multi-class classification and an optimizer as well. We'll train the model for 10 epochs, which means it'll run through itself 10 times. And then we'll evaluate it and check it for accuracy. So let's begin. First, we need to install TensorFlow, which we have already done, and NumPy as well. We already talked about the number of inputs, dimensions, and hidden layers. From here, we'll continue to do that, train the data set based on X and Y values, 28 by 28 grayscale, and that gives us the training shape. And then we'll flatten it, and that is the X being trained, calculating the input dimensions here, 784, flatten the images as well, and then do an output check here. And after that, we prepare the target labels for the model. As already said, the number of classes is going to be 10, and we'll then one hot encode the labels using the Keras library in part. After that, we'll begin to define the structure of the neural network. The first hidden layer learns from the input, or rectified linear units, and the second layer learns from the more complex features. The output generates class probabilities via softmax. We'll use optimizers Atom, and we'll focus on metrics accuracy. Next, we'll begin the learning process using the model fit function to initiate the training loop. And we'll use the X and Y parameters that we've trained along with 10 epochs, so the model will iterate over itself 10 times to help detect overfitting by monitoring a percentage of loss and accuracy during training, not the whole thing. So that part didn't take too long. Now we'll compile the model by defining the loss function, which was the categorical cross entropy we saw up there, and the optimizer Atom metrics accuracy to track, which ensures the model knows how to learn. And at this point, we've prepared the data, the model architecture, and trained the model. So now it's time to evaluate the performance by feeding the testing images from X to the trained model and comparing it to the model's prediction to the true testing labels, which are the Y values. And then we'll look at the final loss and accuracy. And this is just the print statements for what that's going to be. So we're seeing here a loss of about a little short of a 0.01% with an accuracy of about 98, a little bit short of that. I'm sure it would be different if we ran it again. So after this, we've determined the model's accuracy, but it would be nice to do some more test cases. So this first test case calculates the overall accuracy and loss across the entire data set. It's about the same, as you can see. And then the test two, to compare it, the model's prediction to the actual label. This is the fun one. So here we'll use the NumPy libraries and the matplotlib, everybody's favorite matplotlib. Get some good visualizations in here. We'll start with the index. We'll get a sample image and a true label, X being the sample, Y being the true. We'll prepare the image for prediction. And then we'll get that prediction. And then we'll determine the final prediction. We'll display the results. We'll display the image. And we'll also display the prediction of the bar chart. And make a print statement. So here is the true label, which is clearly a 9 without the little hook. And the model's prediction is that it's a 9. Probability that it is pretty high. Yeah, that's a 9. So it looks like the model's working. Let me see if I can just, shot in the dark here. I'll give it one more. I might have to run the entire, yeah, I'd have to run the whole thing, so I can't do it again. But anyway, hope you've enjoyed. And this has been building a simple neural network for classification. Thank you so much now.